In this video, we're studying a surface of revolution created by revolving the graph of the hyperbolic cosine function on the interval -1 to 1 about the x-axis. So there's our curve sweeping out a surface of revolution, and our goal here is to compute the surface area of this shape. So the basic idea is that we're going to slice this surface into thin ribbons, nail down the dimensions of these ribbons, and then add up the area contributions given by our ribbons all the way from the left side of the surface to the right. So in our picture now we have a representative ribbon, and we start to label its dimensions. First, I want to point out that the position of this ribbon can be indicated as x. So that's the horizontal location of the ribbon. And that's a variable quantity going from -1 to 1 as we cover this surface in ribbons all the way from the left end at -1 to the right end at +1. So the fact that this ribbon is located at a horizontal position of x means that the radius of the ribbon is given by cosh of x, because that's just the y value on the curve corresponding to x. Finally, the thickness of the ribbon is given by a small increment of arc that we call ds. And we recall that an arc length increment of ds is given by the square root of 1 plus the derivative of the function we're looking at, so I'm going to call that f prime of x, squared times dx. So in this case, that's the square root of 1 plus sinh squared of x, where sinh is the derivative of the cosh function, and that's the hyperbolic sine function. All right, so now we're going to cut and unroll this ribbon, and that gives us a thin rectangle with infinitesimal area that we'll call dA. And the thickness of this ribbon, that's just ds, and I'll just leave it that way for now because the expression for ds is too long to fit in that space. How about the length of this rectangle? Well, that corresponds to the circumference of the ribbon when it was rolled up, and circumference is 2 pi times radius. So we just have to plug in the fact that the radius of this ribbon was cosh x. All right, so this allows us to write down an expression for dA. The area of this cut and unrolled ribbon is just the length times the width. So I take 2 pi cosh x and then multiply by ds, and I'll go ahead and sub in that expression real quick. ds was 1 plus sinh squared x times dx. So the inside of this square root actually simplifies by using an identity for the hyperbolic trig functions cosh and sinh. As it turns out, 1 plus sinh squared gives us cosh squared, and I'll post a link at the top to the derivation of that fact. So taking the square root of that, I end up with just a second factor of cosh, and this means dA simplifies to 2 pi cosh squared of x times dx. So now we have the area contribution of a single ribbon written entirely in terms of the variable x, and we're ready to add these up by using an integral. So A is just equal to the sum of all the area contributions dA. And this is what an integral does. It just adds up all the continuously changing infinitesimal contributions and tells you what the total is. So I'm going to move the 2 pi out in front when we sub in our dA, and we end up with the integral of cosh squared x dx. And the integration limits here are from -1 to 1, covering the surface all the way from its left end to its right end. Now we can use the fact that the cosh function is even. We can even see that in the picture. It has symmetry about the y-axis. And this allows us to just cut the integration interval in half and then double the result. So I already moved a factor of 2 out in front, and now we're integrating from 0 to 1. Okay, and at this point, there's no secret trick for integrating the square of the cosh function. We're going to have to expand the cosh function using its definition. So I'll post a link to the video where these were introduced. But the hyperbolic cosine function is 1/2 times e to the x plus e to the negative x. If we square that, we get a 1/4, and I'm going to pull that out in front. And now in our integral, we have a product of these two binomials, e to the x plus e to the negative x, multiplied by itself. So out in front, we can cancel those 4's, and we end up with a pi out there. And then we distribute between these two binomials. So e to the x times itself gives me e to the 2x. E to the x times e to the negative x is just 1, because that's e to the 0. And I get another one of those, so that gives me a 2. So I have plus 2. And then e to the negative x times itself is e to the negative 2x. Now we're ready to find the antiderivatives of each of these terms and get a final answer, but I'm out of space. So I'm just going to wipe out this rectangle, and we'll continue up here. So we're finding the area of this entire surface, and that's pi times the antiderivative of this thing evaluated across the limits of integration. So the antiderivative of e to the 2x is just going to give me a 1/2 e to the 2x. If you don't believe me, just take the derivative of that, and the chain rule kills the 1/2. Our second term is just a 2x, and then our third term is a negative 1/2 e to the negative 2x. And we're going to evaluate this from 0 to 1. So subbing in the upper limit here, I end up with a pi times 1/2 e squared. I'm just going to write that as e squared over 2 plus 2, and then minus 1/2 e to the negative 2, and I'm going to write that as a 1 over 2e squared. So there's our upper limit, and then we need to subtract from that the lower limit. And this gives us pi times 1/2 e to the 0, so that's 1/2. But at the end of this expression, I have a negative 1/2 e to the 0, so those are going to cancel out. Then I look at my middle term, and just replacing x with 0, I get another 0. So everything in the lower limit vanishes, and we don't have to worry about that. So just cleaning things up a little, we can just pull a factor of 1/2 out of this entire thing and write pi over 2 out in front times the quantity e squared minus 1 over e squared plus 4. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.